Life first began in the oceans around 3.5 billion years ago, evolving over millions of years from simple unicellular organisms to more complex multicellular plants and animals. Let's take a journey back to explore Earth's early environment and how arthropods were the pioneers in the battle for land territory.
During the early Paleozoic, Earth's landmasses seemed to be a hostile, barren world where no complex life flourished. While predators weren't initially an issue on land, early pioneers faced other difficulties out of the water. Harmful UV exposure, risk of desiccation, lack of buoyancy, and temperature extremes, along with differences in the behaviour of light and sound in air, all made the transition to land difficult. During the late Cambrian, lighter oxygen-16 isotopes from fossil conodons show evidence for a climate that was warmer than today due to higher greenhouse gas levels such as CO2 and methane. However, with the help of plants, the Earth began to see a steady rise in oxygen combined with a drop in CO2. Ozone production in the atmosphere began to occur, leading to a slow reduction in UV radiation and a gradual global cooling.
Colonization of the land by plants is thought to have occurred some 500 million years ago. The first land plants were a bryophyte grade of organization. Liverworts, mosses, and hornworts, with liverworts being the most basal group, grew in semi-terrestrial environments, however remained somewhat submerged in the water at all times. This is because they depended on water for reproduction and had not yet developed any adaptations to fully prevent water loss.
Eventually, fossil records shows an increase in complexity as well as increase in variation through the Silurian to the Devonian, with plants developing vascular tissues, a reproduction system that's independent of water, and spores, which later evolved into seeds. With the terrestrialization of plants increasing oxygen levels and decreasing carbon dioxide, this gave rise to a more habitable environment for any animals leaving the water.
During the mid to late Cambrian, fossil records from locations such as the Burgess Shale and Shenyang show that a rapid rise in complex and diverse multicellular organisms had begun to evolve in the oceans. The increased dissolved oxygen levels allowed organisms to grow larger, and they began to develop shelly parts or hard exoskeletons. They became more mobile and often contained offensive features like stingers, teeth, and claws, or defensive features such as sharp spines or guarded armour. The reason for this sudden evolution is believed to have been partly influenced by a rise in predatory species. Some of these were gigantic for the Cambrian and wielded highly evolved weapons to catch unsuspecting prey, many with keenly developed sensory organs. This made predators such as Anemocarus the terrors of the sea.
However, while this increase in edible plant matter on land may have been one of the drivers behind terrestrialization, this is not thought to be the only selective pressure for arthropods moving onto land. Seeking refuge from predators may have been equally important, particularly for the vulnerable eggs and during their molting process of ecdysis, where they are left immobile for short lengths of time. Many of these early arthropods were well adapted to make this move onto land. Most notably, their tough but mobile exoskeleton allowed for more advanced locomotion as well as preventing rapid desiccation once exposed. This survival suit gave them the ability to temporarily leave the water and take refuge on land. This would have been extremely favorable for survival. Trace fossil trackways from Wisconsin show that hermit arthropods in the late Cambrian, 500 million years ago, may have done exactly that.
In the Cambrian oceans, these early ancestors of modern arthropods had already developed evolutionary adaptations necessary for the survival on land.
To create their hard exoskeleton, secretions from the cutaneous glands were combined with calcium carbonate in seawater, which acted like a cuticle on land and minimized UV damage, as well as giving support and protection from predators. Over generations, this allowed some arthropod species to grow to enormous sizes, particularly in water, where buoyancy aided in supporting their weight. Their jointed appendages allowed for more complex locomotion, and segmented bodies held their capability to evolve into a variety of highly specialized apparatuses, such as claws, legs, stingers, pinchers, and jaws.
New fossil discoveries from marine deposits in Ontario, Canada, show mid-Silurian sea scorpion species, Uranoscorpius brucensis, to have a leg morphology similar to that of recent scorpion species. It can be seen to have a back tarsus segment shorter than the segment before, meaning it could be placed flat on the ground like a foot, allowing these scorpions to stand upright. However, these solidly attached limbs were unable to hold the scorpion fully upright out of the water, unlike the hinged mechanisms seen in modern scorpions. These fossils may be showing us the early stages of scorpion evolution, which would later allow for terrestrialization. Even at these early stages, when threatened or during vulnerable times in their development, these species could briefly haul themselves onto land, giving them an advantage for survival. As plants began to colonize the land, arthropods which ventured onto the land may have started to find a reason to stay, as early land plants produced oxygen alongside providing a moist, sheltered habitat. Arthropods capable of obtaining atmospheric oxygen had the capability to prosper on land and over time specialize into a variety of new ecological niches. To attain this ability, some developed modified gills such as buck lungs, thin arachnids, or some inhaled oxygen through tiny external openings in the exoskeleton called spiracles. These could also be closed when it is necessary to minimize water loss.
Ancestral millipede species are thought to be among the first arthropods to have become fully terrestrialized. Mosses and early vascular plants could have provided a stable food source, safety from predation, and a humid environment in which to live in. To attain oxygen, these early land millipedes contained regularly spaced openings or spiracles along their flanks, which meant submersion in water would have been adverse. A fossil Pneumodesmus pneumani fragment from the late Silurian, found in Scotland, shows evidence for this. However, earlier trace fossil trackways, Diplicnitis and Diplopodicnus from late Ordovician Borrowdale volcanic group in northwest England, show millipedes may have been coming onto land well before this.
Early sea scorpion species are known to have grown to much larger sizes than modern scorpions. Their hard exoskeleton, well-jointed appendages, sharp poisonous stingers, and strong scissor-like claws made them formidable hunters. Early sea scorpions are believed to have initially come onto land during molting, but later their arthropod prey may have tempted them to move more permanently out of the oceans. Trace fossil trackways from Aeolian sandstones in Ontario, Canada, dating from the late Cambrian to early Ordovician, show subaerial locomotion, suggesting that there were some amphibious arthropod species at the time. Arthropods played a crucial role in the development of soils and in nutrient cycling as they dug into and reworked the top layers of soil. The increase in land plants and their gradual move further inland then led to a steady greening of the Earth's land masses and increased the potential territory for evolving arthropods.
Today, arthropods are one of the most successful phyla on land, with insect populations alone accounting for over 70% of all land species. They have evolved into 4 successful classes: Crustacea, which include lobsters and crabs; Myriapoda, which include centipedes and millipedes; insects, which have beetles and butterflies; and arachnids, which include scorpions and spiders such as Elsa here. Arthropods occupy almost every inch of the globe across a wide variety of ecological niches and trophic levels. They have truly become a dominant presence on land.
As land began to flourish with life, Devonian tetropods began to slowly emerge themselves from the oceans. The battle for land domination had begun.